Welcome back, Physics 30. This is the last section in the FM2 unit. So FM2.9, dynamics and uniform circular motion, kind of takes off from where we left off with the FM, I think it was 1.9, the very last section in the last unit dealt with uniform circular motion. But now we look at the forces involved. So use Newton's laws of motion and the concept of centripetal acceleration to solve word problems. So according to Newton's second law, F net equals ma. An object that is accelerating must have a net force. So remember, acceleration and force go hand in hand. And not only that, but they have the same direction. The acceleration is in the direction of the net force. An object moving in a circle, such as a ball on the end of a string, therefore must have a force applied to it to keep it moving in that circle. So that's a key thing to note as well. That is, a net force is necessary to give it centripetal or radial or circular acceleration. The magnitude of the required force can be calculated using Newton's second law for the radial component or circular component. So you can see here F net equals ma. We can treat it as F equals ma. The sum of all radial forces equals mass times the centripetal acceleration or radial acceleration. So recall in the last unit, A, acceleration in a circle, can be determined as v squared over r. So we can take that v squared over r and put it into here, and we get this. So F is equal to mass times v squared over r. Notice in this diagram, so if I was whirling something in a horizontal circle above my head, I'd have to have an inward force. Because remember, the object is going at constant speed, but in terms of velocity, it's changing. So the magnitude is the same, but since the direction is changing, we say that is a change in velocity. Because remember, velocity is a vector quantity. It depends upon two things: a magnitude and a direction. If the magnitude stays the same, i.e. you can see these arrows are the same length, but the direction is changing, so technically it is a change in velocity. If you're going around in a circle in your car going 20 kilometers per hour, you're changing your velocity. Even though you're going 20 kilometers per hour, you're changing your direction. Now, as I mentioned up here, A and F are in the same direction, so as we found out in our previous unit, acceleration has to be in the same direction as the force. And the acceleration isn't causing speeding up or slowing down. It's causing the change in direction, causing it to maintain this circular motion. So you have to be careful with that. The changing velocity and changing acceleration are simply affecting the direction. For uniform circular motion, the acceleration, which is directed towards the center of the circle, as I said, at all times, thus the net force too must be directed towards the center as well. A net force is necessary because if no net force were exerted, the object would not move in a circle but go off in a straight line. So for example, if I could no longer maintain this force here, for example the string breaks, then this would continue off in straight line motion. An object in motion stays in motion in a straight line, as Newton's first law tells us. The direction of the net force is continuously changing so that it is always directed towards the center of the circle. So again, net force directed towards the center of the circle. This force is sometimes called centripetal, and by centripetal we mean pointing to the center. But be aware that centripetal force does not indicate some new kind of force. The term centripetal merely describes the direction of the force needed to provide the circular path. The net force is directed towards the circle's center. The force must be applied by other objects. For example, to swing a ball in the circle on the end of a string, you pull the string and the string exerts that force on the ball. Here, the centripetal force that provides the centripetal acceleration is the tension in the string. In other cases, such as if we're looking at gravity on the moon, a normal force or even an electric force. So in terms of planetary motion, our sun is what is providing the inward force to keep planets in line in the solar system. Okay, if we look at the next page, there's a common misconception that an object moving in a circle has an outward force a center fleeing force, which is sometimes referred to as centrifugal. This is incorrect, though, however. There is no outward force on a revolving object. The term is often misrepresented, too. When you swing a ball on the end of a string around your head, you know that you feel a force pulling outward on your head. This misconception arises when this pull is interpreted as some sort of outward centrifugal force pulling on the ball. But that is not what's happening. To keep the ball moving in a circle, you pull inward on the string, and the string exerts this inward force on the ball. Of course, Newton's third law, action, reaction. The ball is exerting an equal and opposite force on the string, and that is what your hand feels. So it's not some weird centrifugal or central fleeing force. It is simply the reaction force. So hand pulls on ball, ball pulls on hand. Newton's third law right there. If you were to let go of the string at a certain point, the ball, of course, flies off tangentially, so off on a tangent, just like we've talked about before. So if I let go of the string, it wants to fly off. If I let go of it right here, of course, from those vectors on the previous page, it wants to keep on going in a straight line, so it flies off, because Newton's first law suggests that. There's no centrifugal force pointing outward. What happens is the natural tendency of an object to move in a straight line, which of course is Newton's first law. If the centripetal force vanishes, that's the key thing to note. So if I somehow get rid of that inward force, then Newton's first law, object in motion wants to stay in motion in a straight line, tangent to the circle. All right. So let's take a look at this example we have over here. So example, force on a revolving ball. And we're looking at horizontal cases here, of course. Person must exert a force on a string attached to a 0.15 kg ball to make the ball revolve around a circle of a radius 0.600 meters. The ball makes 2 revs per second. Determine the period and determine the speed, and determine what force must keep it there. Now, revs per second, that is frequency, if you recall from last unit. And if I want to figure out the period, the number of seconds it takes to make 1 rev, and you will get this formula sheet, of course, I take 1 over frequency. So 1 over 2 revs per second, and that's going to give me a period of 0.500 seconds to 3 sig figs. B, the speed of the ball. Of course, we're going around in a horizontal circle of some radius. We know the period. So if you recall from last unit, to figure out the speed, V equals 2 pi r over t. So basically it's distance over time. The distance, the circumference it's undergoing is 2 pi r. The time period is period. So 2 pi times the radius of the circle is 0.6 over 0.5. So that's going to give us 7.5398822 meters per second. Could round it off to 3 sig figs though. 7.54 meters per second. And of course, determining the force using the equation that we just found out. F is equal to mv squared over r. So the mass of the object is a 0.15 kg ball moving at a speed of 7. No, I'll take the non-rounded off answer here. All right, that's over r, which is 0.600 meters. All right, so if we calculate that, the force works out to be 14.2122 newtons. Round it off to 3 sig figs, 14.2 newtons. All right, so centripetal force. So that's it, ladies and gentlemen. And so work on that. You should be able to do the assignment now and access your reference sheet. You should be able to do fine. See you again.